Hello students, we have already seen Newton's first law of motion and Newton's second law of motion, in which we have seen that the first law of motion is define force and the inertia, and it is state that for every object which is in moving or which is in rest, it always remain in the same position until unless a force is applied on it. And in the second law of motion, we have seen that the force is equal to the rate of change of momentum. So here we will proceed in the Newton's third law of motion. In Newton's third law of motion, the statement is every action there is equal and opposite reaction. That means if a force is working as in the form of action, so definitely a force is also work against it in opposite direction to compensate it, and that will be called as reaction. So every action there is equal and opposite reaction. In class 9th you have learned this already and many examples you have seen also. So once again we are discussing here. For example, you can see that here is an apple and this is the earth. So the apple is attracted towards the earth. So earth is also attracted to the apple. Okay, that means apple is attracted towards the earth. So apple is applied, earth is applied a force on the apple. So apple is also applied a force on the earth. Okay, so both are applying force on each other, and that force is called action and reaction force. Okay, so what you will find here, you can see that apple fall towards the earth, but earth cannot move towards the apple. And why it is not moving towards the apple, that can be explained by another law called as the law of conservation of momentum, and which is the principle behind the Newton's third law of motion. Okay, so the statement and the rest of the thing of the the law of conservation of momentum, that we will see afterwards. Here we will see that Newton's third law of motion, in which the action and reaction will take place on the body, but many misconceptions are there. For example, as we can see here, the two objects or two bodies are there as A and B. So if A is applying force on B and B is also applied a force on A, so here the force on body B by A must be equal to the force on body A by B in magnitude, but in direction they should be opposite. Okay, you can see that FAB, if it is working in this direction, so FBA is working in this direction, and both are equal in magnitude, but they are opposite in direction. So if one is action, another is reaction. So what we can see here, the force always occurs in pair. The forces always occurs in pair. Okay, that is the first point that you have to clear. Now the second thing is that here action and reaction, you might be thinking that first the action will take place, then the reaction will take place, but it is not like this. Actually the action and reaction both work at same instant. That means it is not there the first action will be there, then after that the reaction will be there. Action and reaction both will take place at the same time. Okay, so this misconception should be not there. And the third point that you have to be very careful in this, that action and reaction works on two different bodies. Like suppose if you are saying the A is applying force on B, that is action. So B is applying force on A, that is reaction. That means if action is working on body B, so reaction is working on body A. Okay, so in such cases you can find that there will be no cancellation in the force. That force will be not cancelled here. Actually the force applied in the magnitude are equal, but that means the action and reaction both are working at the same time in the two different bodies. For example, you can see here, when a man step out from the boat on the bank of a river, the man pushes boat from his foot and the boat will move in the backward direction. At the same time, the boat will apply a force on man, and so that the man can move in the forward direction, or man will be jump out of the boat. Okay, so here you can see that if one force, if you are saying that man is applying the force on the bed, that is the action. So the boat applied the force on the man, that will be the reaction, and both are working at the same time. Both forces are working, that action reaction pairs are working at the same time, and action is in one body, so an reaction will be another body, so no cancellation will be there. You can see the effect of action and reaction here. Okay, that the action, by the action, suppose the boat is moving backward direction, so because of the reaction the man is moving forward direction. Okay, so this way. Here in this example, apple and earth, I will just come after the laws of motion. Here you can see that the acceleration produced on the apple and earth will be different. The forces are equal in the magnitude, action and reaction forces are equal in the magnitude, but we know that the force is equal to mass into acceleration. The force is equal to mass into acceleration, that we know from the Newton's second law of motion here. Okay, so if the two forces are equal, action reaction pairs are equal, so this mass and acceleration, the product of mass and acceleration will be also equal. Okay, that means if the lesser mass will be there, so acceleration will be more, and if the mass is more, the acceleration will be less. That means you can see that the mass of the apple, if you compare with the earth, it is very less, so the acceleration produced on the apple will be very large, and the acceleration produced on the earth will be very small, and that's why the acceleration which is produced on the apple, by what acceleration it is moving towards the earth, that can be noticeable, and you cannot notice because the acceleration produced on the earth is negligible in this sense. Okay, so later we will see in the laws of motion, laws of conservation of linear momentum. Okay, we will see this example once again, which is the principle behind the Newton's third law of motion, as I said to you. Law of conservation of momentum. The statement is, according to this law, in an isolated system, the vector sum of linear momentum of all the bodies of system is conserved and is not affected during their natural action and reaction. Okay, that means in case of an isolated system, that means the no external force is working on that. Consider here we have taken an isolated system. It is said that for an isolated system, whatever change will be there in the momentum, that will be conserved. That means the change in momentum will be zero and momentum will be conserved. Okay, so to explain this and how it is related to the Newton's third law of motion, I have taken here an isolated system, and this is the isolated system of two bodies A and B. The mass of body A is m1, the mass of body B is m2. Here you can see that both the bodies are applying force on each other. Maybe they are colliding to each other for an instant del t time. So you can see that the body A is applying force on B, which is written as Fa in this direction, and the body B is applying force on A, which is indicating here with the Fb, and in this direction. Okay, suppose the velocity initially, body A is moving with the velocity u1 and body B is moving with the velocity u2. This uniform velocity, suppose these two are moving with the uniform velocity u1 and u2, and in this case, when they collide to each other, after that the velocity will change and body A is moving with velocity v1 and body B is moving with velocity v2. Suppose acceleration produced on A is a1 and acceleration produced on B is a2. So these are the things, or once again I am explaining to you, I have taken an isolated system in which the two bodies are there, A and B, of mass m1 and m2 respectively, moving with initial velocity u1 and u2 respectively. After collision they are moving with velocity v1 and v2 respectively, and the A is applying force on B, which is indicated with the FA, and B is applying force on A, indicated with the FB. Acceleration produced on body A is A1 and body B is A2 here. Okay. Now, what we have learned by the law of conservation of momentum, that the momentum before collision, momentum will conserve. So momentum before interaction, you can say, before collision you can say, momentum before is equal to momentum after collision or after interaction, whatever you want to say you can say. Okay, momentum before is the total momentum is, that is mass m1 and initial velocity u1. This is the momentum of the body A. Then the momentum of the body B is m2 u2. So this is the total momentum of this system before collision. Now after collision you can see that the momentum is m1 v1 for body A and for body B m2 v2 it is. So if you just check here, you will find that this, we will transfer m1 v1 this side and m2 v2 this side. Okay, u2 this side. So it will be m1 u1 minus m1 v1, or it is m2 v2 minus m2 u2, or we can say here m1, if I am taking m1 common, I am just writing v1 here and u1 afterward changing the sign, so the negative sign will come here. You can see that negative sign I have taken out, so m1 v1 will become positive here and m1 u1 will become negative here. Okay, similar way you will find we have taken m2 here, so v2 minus u2. What you can say, this is the change in velocity, mass multiplied with change in velocity. Here also mass multiplied with change in velocity. That means what it is, this is the, you can see change in momentum in the first body and the change in momentum in the second body. So here we can write, now this is, let the change in momentum in body A it is, this is indicating the mass into change in velocity, that will be the change in momentum in the first body, that is the body A, and here the change in momentum in the body B. Okay, so that means what we have observed here, we can observe del PA plus del PB is equal to 0. If you take this del PA this side, so it will be del PA plus del PB is equal to 0. That means change in momentum in body A and body B, or you can say in this isolated system, is 0. Change in momentum is 0, that means the momentum is conserved here. The momentum is conserved here, because we have seen that the change in momentum will take place for this instant del t, for this duration del t. So if you just, this is the equation, this, suppose this equation 1, in this equation we will divide this is minus del PA is equal to del PB, the change in momentum in the body A is equal to change in momentum in the body B, if you just divide this with the time del t both the side, there will be no change in the equation or no effect in the equation. So it is minus del PA upon del T, and this is del VB upon del T. So according to Newton's second law of motion, we know that the rate of change of momentum is equal to force. So here the rate of change of momentum is equal to force. We can write this FA, we can write this FB here. That means the force applied by A, or the force applied on A by B, is equal to the force applied on B by A. Okay, that means the two forces, you can see here, these two forces are equal in magnitude but opposite in direction, and which is the statement of the Newton's third law of motion, that every action there is equal and opposite reaction. Okay, so here you will find these two forces are action and reaction force, which is working at the same time, and these forces are equal in magnitude, opposite in direction. So this is the Newton's third law of motion, can be explained by the law of conservation of momentum, or the law of conservation momentum is the principle behind the Newton's third law of motion. We can say both way. We got the relation here, minus FA is equal to FB. This is minus FA is equal to FB, and we know that the acceleration produced on this body A is A1, the acceleration produced on the body B is A2 here. Okay, and we know that from the Newton's second law of motion, the force is equal to mass into acceleration. So force produced on body A can be written as, this is written as M1 A1, and this can be written as M2 A2. If you just see the magnitude, I'm not taking the direction here, if the magnitude if we are taking, that will be equal to M1 A1 and it is equal to M2 A2, or you can say M1 upon M2 is equal to A2 upon A1 if M1 is less than M2. That means the lighter body is M1, the first body A, and the second body B is the heavier one. So what you can see here, the M1 is less than M2, so the A2 is less than A1. A2 is less than A1. That means the acceleration produced on the second body is less than the acceleration produced on the first body. So what we have observed here, we can observe here that the acceleration produced on the lighter body will be more than the acceleration produced on the heavier body in the action reaction pair. Okay, and that's why I have explained you the example of earth and apple, in which the apple is having the less mass, so the greater acceleration will produce on the apple in comparison to the earth, and that's why you can see the movement of apple towards the earth, but you can't see the movement of earth towards the apple. Okay, that is the thing. One more example we can see here of the law of conservation of momentum, that is the recoiling of gun. In recoiling of gun, initially what you can see, the bullet, when the bullet is loaded with the gun, and initially suppose the mass of the gun is M2 and mass of the bullet is M1. So the total mass of total mass of gun with bullet is M1 plus M2. Okay, and initially it is in rest position, so no velocity is there. This is in rest position, no velocity is there. Okay, so when the bullet is fired from the gun, bullet move in forward direction with velocity v1, and so that the gun will move or gun will recoil in the backward direction with velocity v2, and that force can be experienced by the soldier. Okay, and that will be work on the shoulder of that soldier. Okay, so you can see that In such situation, what we have seen, the momentum, initial momentum is m1 plus m2 multiplied by 0, because 0 velocity is there. The gun which is loaded with the bullet will be is in rest position here, and when it is fired from this, the bullet is fired from the gun, so the momentum will become m1 v1 plus m2 v2. And we know that from the law of conservation of momentum, the momentum before and the after the incident will be same, because here you can see that m1 plus m2 is 0. M1 m2, the mass of this the gun and the bullet, and the velocity is 0 here. So what you will find now, you will find that m1 v1 must be equal to m2 v2, and that means this is the, simply you can say, the momentum in the gun will be equal to the momentum in the bullet, but this will be in opposite direction. This will be in opposite direction. If the bullet is moved forward, so gun will be moved backward. So bullet is suppose action, so gun is a reaction force here. Okay, and that is also means that is also the we can explain this phenomena by the Newton's third law of motion also. Okay, one more example you can see here, that is the rocket propulsion, and it is very interesting example. In the rocket propulsion, whenever we propel the rocket or launch the rockets are having many chambers like this. So in these chambers, the fuels are there, and at the top of the top of this rocket, the object which we have to project is kept here. Okay, so what happened, this fuel, when it is burned, it will move with great velocity in this direction, the backward direction, with a great velocity, so that initially when it is not moving, that means when rocket is kept as it is with the fuel and it is not moving, so initial velocity of this whole system is 0. That means, and if the fuel start burning and the fuel is with the great velocity, it is ejected out from the chamber. So what happened, the momentum is work in this direction, which is the momentum of this fire, momentum of the fuel, which is moving out of the chambers of the rocket. Okay, and so that with that momentum, the rocket can be propelled in the forward direction, the rocket can be launched in the forward direction. So as this chamber will be the fuel of this chamber will be finished, this chamber will be thrown out somewhere, like means you can read about this in a very detail. Okay, so it can be thrown out, so the next chamber fuel will be start burning, and so that if it is completed, the burning of this fuel of this chamber is completed, so this also will be thrown out, or you can say simply can be dropped somewhere. Okay, so is that way you can see that at last wherever the target is there, the mass of the total rocket will be very less. Because the mass will be very less, the velocity will become very high, and so that this can be achieved. That means the object which is projected, suppose a satellite is there which we have to project it, or which we have to install in an orbit, so we can install this satellite to that orbit by this rocket. So this way the law of conservation is working in this case also. Or you can say simply the burning of the fuel, if you are taking as a action, so the movement of the rocket in the forward direction you can take as the reaction. Okay, so the both the means many phenomena you can explain both way, whether it is by the law of conservation of momentum or by the Newton's third law of motion.